So just as we can maximize what we're looking for, we can also minimize. Say we're designing a can that has a volume, imagine that's a can, a volume of 500 milliliters. And our volume formula for a cylinder is pi r squared h. And in this instance, let's assume it's the same like density as water, so that milliliters is equal to centimeters cubed for easy conversions. And we also have our surface area of this cylinder, so 2 pi RH plus 2 pi r squared. We want to minimize S given our volume constraint. So we can solve our volume for H. H is equal to the volume over pi r squared, which is equal to 500 divided by pi r squared. Now, one quick thing. Our volume is our total H, and this is R. Our surface area is going to be this circular area, and this circular area, this circular area, and this circular area. That's why it's 2 pi RH plus 2 pi r squared. So anyway, we have our H. Now we can plug that into our surface area. S is equal to 2 pi r times H, 500 over pi r squared plus 2 pi r squared. S is equal to this pi cancels, and this r cancels. 1000 over r plus 2 pi r squared. Now we can take the derivative, ds by dr, and with the power rule, this is 1000 over r, or 1000 times r to the minus 1, so that would be minus 1000 over r to the negative 2. Minus 1000 times r to the minus 2, which would be 1000 over r squared, and this would be 4 pi r. And now we set that equal to 0, so we have 1000 over r squared plus 4 pi r is equal to 0, and we're going to solve for r. So 4 pi r is equal to 1000 over r squared. R cubed is equal to 1000 divided by 4 pi is equal to 250 over pi. R then is the cube root of this, 250 divided by pi. That's our R. H then was 500 divided by pi r squared is equal to 500 divided by pi times this quantity. Let's actually solve for this real quick. So when we plug this into a calculator, we get r is equal to around 4.3. So that would be 4.3 ... squared. And when we plug this into our equation, 500 over pi times 4.3 squared, we get approximately 8.6, and these are centimeters because we made that easy conversion. That milliliter is basically a centimeter cubed. We could take our second derivative now of S which would be 2000 over r cubed plus 4 pi. And we're plugging in the value that we got for r, 2000 divided by the cube root of 250 over pi cubed plus 4 pi. These cancel. That's 2000 divided by 250 over pi plus 4 pi. And that's 2000 times pi over 250 plus 4 pi. 2000 divided by 250 is 8. So we have 8 pi plus 4 pi is equal to 12 pi. That means that this is greater than 0, so it's a local minimum, and it's concave up. So we have our R value and our H value. What is the volume then? What is the minimum volume? Well, we could do pi times 4.3 squared times 8.6, and our volume is approximately 500 centimeters squared cubed, as we said as our constraint. So these numbers work out. It's approximately 500 due to rounding errors. Our surface area then, what was our surface area? We said it was 100 over r plus 2 pi r squared. So we can plug that in. S is equal to 1000 over r plus 2 pi r squared. My mistake, it's 2 pi rh plus 2 pi r squared. So now we plug these values in. 2 pi times r was 4.3 times h is 8.6 plus 2 pi times 4.3 squared. Our surface area then is approximately 348 centimeters squared. And this is the total surface area, so the total area of the can, this total value, this plus that area plus that area. And that's the minimum given the constraint. Anyway, thanks for watching.